Today we're going to go over a torque problem in two different ways and get the same result. What are the two different ways? Well, there's two different ways to think about torque. And they're equivalent, really. But one way to think about it, and this is what we're going to do in the first problem, is the first solution is to say, you can find the torque if you take the magnitude of the force involved in the torque times the component of the r vector that's perpendicular to the force. And that's what we're going to do in the first. And then in the exact same problem, we're going to think about it in a different way, which says you can find the torque if you take the distance of the r vector times the component of the force that's perpendicular to the r vector. Okay, so let's get into the details of the problem. So in this one, we're told the torque associated with this. So Luis is basically exerting a force on some wrench that's some distance from the axis of rotation. So let's draw our r vector, which r doesn't stand for anything, as you've heard me complain. There's the r vector, and it's a vector it's a distance or length vector that goes from the axis of rotation to wherever the force is applied. And then our vector is already shown here. So this is where Luis, it says he's pulling down on it. And we already know the torque is 13 Newton meters in the negative direction. And the question is what is Luis's force? Okay, so other things we're told that r is 37. So we know this distance is 37. So let's jot that down. Oh, I want it black. R is 37 degrees. No, 37 degrees, 37 centimeters. But because we use Newton meters for torque, not Newton centimeters, we want to think of that as 0.37 meters. Okay, and then our angle is 30 degrees. But what angle? In this case, it's this angle is, you know what, that's going to get in the way where I want to draw it. So we're just going to say we know that angle is 30 degrees. Okay, so first way we're going to solve it is we're going to think about, okay, we're not going to mess with force. Force is what it is. That's what we're going to solve for. But we want to get the component of the r vector that's perpendicular to the force. And the way you do that is you draw your line of action. And it's just a line that goes in, it's oriented in the force, and it has, you don't need to know the name, except that I'm going to call it the line of action. But I'm not going to ask you to define what the line of action is. And the way you get this r perpendicular is you go to your, let me do blue, you go to your axis of rotation, and then you draw a line that basically goes from there and is perpendicular to your line of action, and that is r perpendicular. And that has its own little nickname. R perpendicular is called the moment arm. Moment is another word for torque, so you could think of this as torque arm. Now, hopefully you're seeing there's this right triangle that's made up of r and, well, okay, not F, the line of action and r perpendicular. And we know that angle. And we know r. So hopefully you're thinking trig, because that's what we're going to do. We're going to use trig to determine r perpendicular. We can't measure directly. There's no meter stick. There's no scale. So we're going to use trig. So let's remind ourselves how we do that. So I see that r perpendicular is adjacent to the given angle. That's going to be cosine. So cosine theta, just a little review, is going to be the length of your adjacent side of your right triangle divided by the hypotenuse. Well, in this case, cosine theta is the adjacent side is what we're after. It's that r perpendicular, or the moment arm, divided by the actual length of r itself. Rearranging, I can say, oh, r perpendicular is equal to r cosine theta. So that's what we're going to put in. That's how I'm not actually going to solve it, but think about it. So torque is going to be F, and now we can express, given this angle, that r perpendicular is r cosine theta. So we're going to write that down. Whoops. Let's back up. R cosine theta. I guess I'll put a little dot there because I left a space. R times cosine theta. Okay, now we're going to stop there because you're given the torque, you know what R is, and you know the angle, so the only thing you would solve for, you would rearrange and solve for F, and that's how you would solve for that. Okay, let's do the exact same problem with a little bit of a different perspective, which is now we're going to think about keeping the R vector, whatever that length is, and we're not going to mess with that. Instead, we're going to think about what part of this force is perpendicular to the R vector. So I'm going to draw my little box. And now I'm going to think about resolving or breaking down my my F vector, my force, into its components. Well, in this case, I only really care about the perpendicular part. But 1 second, the dogs are going crazy. Okay, the dogs were keeping me safe from the mailman. Good job, dogs. Okay, where was I? Oh, yeah, so there basically is, we want to break this force vector down into its perpendicular part. Actually, I don't really care about the parallel part, but let's just, so there's F parallel. That doesn't do anything in terms of torque. That pushes the wrench into the bolt, but it doesn't result in the twisting action we want to make this wrench rotate. It's all about F perpendicular. Now, I have another angle right here. Sorry, a right triangle. So I need to know that angle. Well, oops, sorry. Okay, I just had a nice call with my son, so I'm a little, where was I? All right, well, we're going to solve this same problem, but we're going to have a slightly different aspect to it. Oh, that's right. So we're thinking about, instead of saying, torque is the force times the moment arm, we're going to think of torque as the R distance times the component of the force that's perpendicular to that. Okay, so now how do I get that angle? And now I can't remember what I was saying, but I'm not going to start this video over. So it turns out that this angle is the same as that angle. Now, how do I know that? Well, because I remember from our idea about ramps, just real quickly here, and again, well, there's no again, but just a reminder is if I want to get, so again, this is not related to torque. This is just like, how do I know that angle is the same as that angle? Well, it kind of feels like it's the same angle, and it is the same angle, and let me prove it to you in the context of what we did on, well, let me remind you, I'm not going to prove it, but when we had something on a ramp and we had gravity was straight down, as it always is, to the center of the earth, but we wanted to get the different components of gravity, that there's a part of gravity that acts down the ramp, and there's a part of gravity that pulls the object into the ramp. And so this we called Wx, and we called, that's the component parallel, this is the component that's perpendicular, Wy, because we had our x, remember we had our x and y axes like that, and we said, look, this angle is the same as that angle. Now I'm not proving that to you, I'm just reminding you. And if you look carefully, this is essentially the same setup. This would be analogous to our ramp angle, and this would be our angle between the gravity and the negative y-axis here. So anyway, that's what it is, okay? So we got our triangle there, so let's figure out what F perpendicular is. So I've got my right triangle there, and this is the adjacent side, and this is the hypotenuse. And so cosine theta equals adjacent over hypotenuse, or in this case, cosine theta is F perpendicular over F. And that means, rearranging, I can say, by multiplying both sides by F, that F perpendicular is F cosine theta. So that's going to go up here. And so torque is going to be equal to R times F cosine theta. And we're not going to solve it because I know, but you can solve it. I'm not going to solve it, but it's solvable because we know the torque, we know R, we know the angle, and the only thing left to solve for is F. Well, if you look up here, these are the same exact things. So you will get exactly the same answer whether you want to do torque is F times the moment arm, or whether you want to do torque is R times the component of the force that's perpendicular. It's the same way. Now, personally, I think this is a little more intuitive to me. I just see this right triangle here, but this one will work just as well, and it depends sometimes on the context and the angle that you have to work with. That's what we did today.